So looking good. Okay. Yeah. So, I mean, the good thing right now is to speak right now and not later is I'm not the one person that stands between you and the beer. At least in Germany, that's a very dangerous place to be. I know you guys and girls are a lot more polite than Germans on average, but still, I don't want to be there. So I'm just between you and your coffee, which is still a risk, but okay. Having said that, this is at least a 1 hour talk. So I'm again in a bad position. So, but this talk consists more or less of 3 parts. The first part is to understand the problem and why we have to do things differently. So we will manage to talk about that for sure. The second part is more about some solution ideas. There is no one size fits all, so they're just pure ideas and so on. I hope we will manage also to get through those ones. And the third part is a bit about broadening the options so that you have more options to design your solutions. Probably we will just be able to briefly touch those ones or even skip them so that I just try to pull that together in a single sentence or something like that. We'll see how it manages. So I will look a little bit on the time and then see. Let's see if this one also works. Yeah, great. That's so cool. Okay, my name is Uwe Friedrichsen and I work at Codecentric. And yeah, if you want to reach out to me via Twitter, so use the handle, Ufried. If you want to download the slides from this talk, go to my speaker deck account, also Ufried. Or if you want to read my blog, go to ufried.com. Well, okay. But functional resilient software design. The good thing is that this talk is after David one, because we had some things in common, some themes in common, and so you will see that there are some things which hopefully will line up in some way. So first question is then here resilience. What is resilience? And if you go to a dictionary, you get something like, yeah, recovering from an adverse situation like illness or something like that, quickly and nicely, or for material to resume to its original shape, like a spring that you bend and then it goes back to the original shape and so on. I say, yeah, that's nice, but what has it got to do with IT? I mean, we build IT systems and not something which gets sick all the time or whatever. And we don't bend our servers and so on. And there are several ways to approach this question. Here's one. If we talk about IT, in the end, we always talk about systems in production. What do I mean with that? We don't do IT just for its own sake. I mean, we would love to, but unfortunately there's this thing with business value, and by the way, business value is a lot more than just creating some features or something like that, but we want to create business value, so some kind of value with our systems that we create. But we only create this value if those systems run in production. Systems in development, well, can be fun, sometimes they're not, but they don't create value. But that's not enough. They need to be available. They need to do what they promise to do. Otherwise, they don't create any value. Okay, now you might say, well, where's the point? Buy some high availability hardware, or infrastructure, and so on, clustering solutions, blah, 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 and we're done. And yeah, that was the way to go for many years. Unfortunately, meanwhile, we're no longer in the situation that we mostly work with monoliths which more or less don't talk to each other. These days, basically every system landscape we're working on is distributed, highly distributed in some way. And distributed systems, well, David already mentioned it, and I mean the background is deliberate. Werner Vogels, the CTO of Amazon, nicely defined distributed systems in this way. Everything fails all the time. Well, and why does it happen? I mean, that's very different from single process situation. And it doesn't happen because people are stupid, but because we have some failure modes in distributed systems that simply do not exist inside a process boundary. My peer does not respond. Or it responds or not, or it does or not. We don't know. It's a little bit brittle, so omission failure. Or it responds, but unfortunately, way too late. So the arch enemy in distributed systems, latency, kill your system landscape quicker than you can write down timing failure. And response failure is response, but unfortunately, the response is not the one that you expected. Or Byzantine failures, yeah, well, it went amok. We have no clue what that system is doing. And all these things happen in distributed systems. And now this still sounds a little bit abstract. And so if we go a little bit closer to it, how it affects us as developers, so we have a situation that somehow some important information never gets to its place, or it's incomplete what arrives. Or it arrives multiple times. We just seen the example from David, or distorted, especially if you're sitting there and say, yeah, I'm smarter than the standard guys, and I invent my own protocol. I still see people trying to do that. Or delayed the message, we had it out of order, so the withdrawal arrives at your system before the deposit, and well, logically, unfortunately, the deposit actually happened before the withdrawal, and how does your system handle that? Or out of sync local memory, so that the truth in this one node is different truth than in that node. And there is no thing like global truth in distributed systems. So every node has its own truth. And as we are as humans, I mean, every one of you, including me, we have our own truth and our own partial information about some event which happens out there. And so, yeah. And it can also lead to situations where things that are no-brainers inside a process boundary become really hard. So time and ordering happens before. Not solvable in some situations. Or consensus, what is right? Not solvable in some situations. And all these other things. I mean, Nancy Lynch wrote a nice paper back then. She's professor for distributed system, and said, well, here are 100 things which are no-brainers inside process boundaries, which simply do not work in distributed systems. Well, okay. So these things do not happen once in a while, these failure modes. They happen regularly. So Murphy is strong in distributed systems. I think Murphy was born in distributed systems, and he developed very well in there. And then in a normal case, they happen more often than you would expect them to happen, and they're not predictable when they're going to happen. And it's not getting any better, as some people sometimes hope. I mean, we have cloud-based systems, and public cloud becoming more the norm, meanwhile, which means scale out on non-high availability hardware. Well, but your solution must be highly available too. Service-based architecture, so distributed by default. Zero downtime at the same time, so your users do not accept any downtimes anymore. 24/7 is a new normal. Mobile and IoT, multiplication of communication peers across unreliable network connections, social web, unpredictable load patterns, blah, 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 blah. So, yeah. So in terms of resilient software design, we can no longer try to avoid failures from happening. We have to embrace them and deal with them. So that my definition for resilience is something like, yeah, trying to handle adverse situation, unexpected adverse situation in a way that hopefully the users don't notice even that something went wrong in your system, or in the not so good case that you have some kind of graceful degradation of service, so that, yeah, you still can answer, but maybe it's not as good as it would be in a perfect situation. Okay, so much about what resilience is and why we need it. Usually that would be 90 minutes in a workshop, so if you're not completely convinced, bear with me. Let's just assume you were convinced right now and say, yeah, we need that. We need to do something about resilience in our systems. And how do you learn about that? I mean, say, yeah, I have to pick that topic up, and so let's read some literature, and there are some back pressure here, and there's some circuit breaker there, and there's some bulkhead over here, and so on and on. And maybe you said, yeah, well, let's do a training or something like that. And maybe you go to a training like I did in the past about resilient software design. And when I started discussing, I said, here are some kind of categories. So there's some core decisions that really influence all the rest what we're doing. Then there's the core fault tolerance cycle, which says, first we have to detect if something went wrong, and then hopefully we can immediately recover from that, fix it immediately, or at least mitigate the problem. Then there's some treatment, saying, okay, here is try to eradicate some of the root causes. There's never one single root cause in a distributed system. There's always a combination of root causes. So try to eradicate some of them. Some complementing patterns, making things simpler, like things like idempotency, which you mentioned before, and then prevention patterns, reducing the probability. We are no longer in the domain of deterministic systems. Distributed systems are non-deterministic. They have probabilistic properties, always. And then I discuss some of the patterns. Here's a selection of patterns. We do not discuss all of them in the workshop. That would be complete overkill. And they're not complete, but anyway. And then there's something interesting which I quite often see then, when people try to digest that stuff. It goes like that for most software engineers. So go through that. Here's the core stuff. That's a bit like theory, or it's obvious, or blah, blah. Where's the juicy stuff? Where's the juicy stuff? And then detection recovery pattern. Hey, that's cool, that's cool, that's cool. Can we turn that into a live coding session right now? Because that's real hands-on stuff here, something we can do right now. And mitigation patterns, that's also more cool stuff. So yeah, we love that, we love that. And it's understandable, that's really hands-on, graspable, yeah, that's cool stuff. Treatment, well, yeah, that's one-off, so bug fixing, go away. And complementing pattern, yeah, it's okay. And these prevention patterns, yeah, they're a little bit tricky. They're not so easy to implement. So later. Okay. So if we put that discovery into a graph, saying, yeah, something like that. So core pattern, nah. Detection, recovery, mitigate, yeah, cool. And the rest is, so. The point is now, if we look at the actual relevance for system robustness, it's a bit different. So complementing patterns are usually more important than most people think that they are. Because if you don't get them right, well, you have a lot of trouble with the rest. Prevention and treatment, that's okay, more or less. These are important, but not as important as most people think. That one is important. And the point is here, if you don't get that right, then all the rest doesn't matter. It won't save you. All these other cool patterns won't save you if you get them wrong. And this is hard. This is really hard stuff. So, well, looks like we have a little problem here. So, let's look at these strange core parts. What are they? What makes them so important? Okay, here's what I usually tell in the workshops then. Core part. The first thing which is really relevant is isolation. Isolation is a core principle of fault-tolerant software design. I mean, fault-tolerance software design and resilient software design, they have huge overlap, and in the basics, they are more or less the same. Resilience does a little bit more than fault tolerance alone. But we're here on the same common ground in the union. And the core idea of isolation is your system must not fail as a whole. It must not. And therefore, you split your systems in parts and isolate them. You isolate them from cascading failures. A cascading failure is a failure happening in one part of the system and then spreading out to other systems. This part goes down and it tears down the other parts. Again, David had some very nice images about that. You know what we were talking about. So, and we don't want that. And therefore, we try to isolate the system parts from spreading failures. And that's the foundation of resilient software design and fault-tolerant software design. Do this isolation. And how do we implement that? We use a pattern called failure unit. Failure unit, or also known as units of mitigation. And we create then some bulkheads between these functional slices of the system to isolate them against each other. And bulkhead is not necessarily a thread pool, as some people think. There are lots of ways of implementing bulkheads. So it's just these things that avoid failures from spreading. Thread pools are, in some context, one way to do that. And on the technical level, we have some choices how we create these failure units. Can be a microservice, can be actors, it can be then coroutines, it can be micro, whatever. And yeah, these impacts a bit how you will do the rest of it, but the core part is what functionality do you put in which of your failure units? What's in here, what's in there, what's in there? And that's a pure design issue. There's no technology for that. That's just brain power, that's thinking, that's slicing your system. The functionality, not your technology. And that's hard. That's really hard. Now you might say, stop, Uwe. No. We are slicing functionality the whole day. We know how to do that, right? We slice things, tear it apart into some kinds of methods and classes and functions and modules and blah, 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 blah. We do it all the time, so where's the problem? And, well, how do you avoid this situation? There's an external request to service A, and service A requires to call to service B to complete its task. Some part of the functionality that is needed to complete service request is in service B. And we also had the situation in the talk before, but in general, so if we do that, if service B is down, service A can't fulfill its task. And we see that all the time. Very familiar situation. That's broken isolation. Or we have a situation like external request to the service, and then we create a service. Whoa. That's a big one. That's a big one. That's a little bit too much for a little. It's not a microservice, not even a macro service. That's a gigantic service which would create. So let's split that up. So create a little bit smaller services which take over some functionality. And well, that's still a little bit big. So split it further up until you end up with a design like that. Probably have seen that too. Unfortunately, there are a lot of internal remote calls that you need to answer the external call. And yeah, likelihood that something breaks grows with every request in there. And additionally, latency will also grow. So your availability is probably not too good. And then you say, well, you've learned that in production, that this design was not the best idea, and then you try to put things a little bit more together again, and eventually end up with something like that. And yeah, but we said for isolation, we wanted to split up that whole thing in some way and isolate things against the other. This is not split up. So isolation is, again, broken. Done. It's not that easy. But say, no. We have our best design practices. We have all these well-known practices. We know how to do that. So let's apply all that things like divide and conquer, functional decomposition. So that's what we get taught in computer science 101, and that's what we learn all the time. Usually, I mean, we have it even in our IDEs, extract method and so on. So refactoring patterns are going, all what we do all the day is functional decomposition usually. We learn that, we know that. You can wake me up at 3 a.m. and I know how to functionally decompose things. Or we had that, try, don't repeat yourself, go to a code retreat and take out your bingo card, and probably it will not take as long as it takes as David to mention Kafka, that somebody on the code retreat starts to talk about dry, don't repeat yourself. Or if you're an architect, I work as an architect quite often, and so I'm allowed to say, so we brace our little finger and say, yeah, well, we design for reusability because that's how we do things. And of course, the holy grail of our software architecture for the last 40 years was layered architectures and so on. So we know how to do our stuff. We know how to split up things. And then there are some agile folks who say, no, we don't do any of that. We have emergent architecture, and we just do our TDD cycle, and with the refactoring, everything will be great. But I mean, TDD is a cool idea. And if you don't have any other means to drive your design, do it. But implicitly, you will always use what you have learned in your education to drive your refactorings, which is the stuff. Now let's apply that stuff to our design. You know what's coming. That's reusability and dry. That's the reusable service. So that's our reusable functionality that we need to call to execute service A. If our reusable service is down, every reusing service is dead, per definition. You can have 100 million circuit breakers in between, or event streams, or whatever. It's functionally dead, because coupling is defined by the maximum of business-level coupling and technical level coupling. So if you have a tight coupling on the business level, your technical level won't save your ass. It will only do that if you have a low coupling on the business level. So, and reusability is a very tight coupling. Actually, the tightest coupling available. And that's, well, structured decomposition, so divide and conquer, layered architecture is here. And now you figure out, oh dear, I ended up with, high coupling and low cohesion, which is exactly the opposite of what we try to achieve. And so we try to fix the cohesion part at least, and we're back here. Welcome to distributed hell. The thing is that all these design techniques, which are really useful inside a process boundary, do not work very well across process boundaries, because this remote call with its non-deterministic properties changes the forces so massively that we have to come up with very different designs to satisfy this new force that we see here. But of course you don't give up. I say, well, come on, one more shot. I've got caches. I've got caches for the rescue. Caches for the rescue. So put a cache in here, and if that server is down, we can go to that cache and still satisfy the request, which is not a bad thing to do. Really, caches are very useful in distributed systems, and you will use caches in distributed systems. But if you use them all over the place, caches come at a price. Caches cost resources. If you have to copy data all around, all the time, lots of data, it will easily consume all your existing bandwidth. And you have these stale issues that they're always out of sync sometimes if you information, so eventual consistency and so on. And yeah, so again, whatever you gain, you pay for. So there's a price in caches. And so my statement here is, do you really think that copying stale data all over your system is a suitable measure to fix your broken design? So, I mean, caches are valuable, but they're not a band-aid, a general band-aid for a messed up design on a functional level. That's the key point. So, sorry, caches are not the rescue. So the message, and that was is the end of the first part, more or less, is, okay, what we've learned is we have to relearn functional design, how we split up our business logic, our functionality for distributed systems. These remote connections between the system parts are such a powerful new force, this non-deterministic behavior which we get from them, that we have really to learn completely different forms of design. And the bad part is our education usually does not tell us how to do that. There are no courses about that usually in most computer science educations. But Uwe, if you're standing up here, come on, give us a silver bullet. So, what's the fix? What's the fix? Sorry, silver bullets are still out of stock. You can look them up at Amazon. It's not available. I did that once, and at least at Amazon.com they have some sense of humor, so it's really not available. So, image of yeah, we don't know when it will come back in. And if Amazon doesn't have it, we all know nobody has it. Okay. So, maybe some crash course, some checklist, something which we can use next day, tomorrow, or Friday to fix all our stuff. Again, it's not easy. It's hard work. Design is hard work. It's an unsolved problem for more than 50 years. David showed the Parnas paper, and there were a lot of great papers at that time, because that was the time when the old mainframe systems became that big that they figured out, hey, we better have to figure out how to slide that functionality better, or otherwise we're screwed. And so they started with that problem, and basically that's what where we're still standing. We never solved it. We're still with all these great ideas from the late 60s and the early 70s, and we didn't advance it. I mean, even domain-driven design picks up all these old ideas in the end, and that's the current fashion. I mean, domain-driven design is the good thing, so if you don't know it, grab it and learn about it and visit the community and so on. But it's nothing really groundbreaking new in there. So, and again, no shortcut. The only thing that I can offer you here is a few guiding thoughts, hopefully bringing you into the right direction. And if I think about functional design for distributed systems, it always brings me back to the foundations of good design. These things from the 70s, these ideas, high cohesion, low coupling, separations of concerns, so on. The problem, and these are really crucial across process boundaries. The problem is, whenever I talk with people about it, I say, yeah, we know high cohesion, low coupling. Yeah, we know separation of information. Yeah, sure, we know. Come on, go to the next thing, which is more interesting. Then I say, okay, show me your design. I look into the design that people created and say, well, there's high coupling, there's no separations of concerns in, and your information hiding is also screwed up. So knowing what something is does not mean that you know how to apply it. Knowing 20 patterns does not know how to apply them, and so on. So, by the way, also a problem with domain-driven design. There are a lot of good ideas and patterns, but I've seen a lot of designs which claim to be domain-driven and which were actually structured design, entity-driven designs. So they just used a new terminology and did the stuff that they always did. Because it's hard to grasp these ideas. So really understanding how to create high cohesion, low coupling. Take your time. Really think about it. It's hard work. Because, again, all our education tells us how not to do that, unfortunately, at least across process boundaries. Still poorly understood. If you can solve that, great. And you have probably solved 99% of all problems that we have in computer science. And what could help a bit, not the panacea, but can be useful. Understanding your organizational boundaries, not your org chart. Org chart is always broken because it's political, so it's shaped by company politics and so on. But your process organization, or usually also not the process, but your shadow organization, of informal communication paths, because they're usually quite efficient and they have these cohesion boundaries or coupling boundaries, so that these units which tightly work together have high cohesion and they have very interfaces with low coupling to the other units and so on. And it can give you an idea, if you understand what's going on there, how to shape your systems. Also, starting use cases and flows. So David said customer journeys. It's another concept which goes into the same direction. So the magic for good slicing lies in the behavior of the system, not in their state. Because that what shapes what calls need to be made, who calls whom and so on. That's the behavior of your system. If you're able to bring as much as possible from one user interaction or from one use case into one part of the system and do not need to go out to other parts of the system, it's better for you in terms of availability in distributed systems. Again, we have counterforces. There's a price to pay for that. But that's a better starting point. Most people still have their entity relationship diagram. I mean, these days we call that domain diagram, but basically it's the same thing. We just used no terminology. If you really understood domain-driven design, you know that there's different things, but in most cases, people do not really understand them, so you still have your customer and your order and your product and so on, and. So entity-driven design. And, but there's some other things. So I want to search for something. I want to check out something and so on. This is this vertical thing and so on. Yeah, there is it, domain-driven design. But again, also learn how to apply it correctly. And if you go back to the original book from Eric Evans, read the second part, not so much the first part. The first part is more about how they did object-oriented design in the early 2000s, which is okay-ish, but which can lead you in the wrong direction in some places. And last but not least, repeating, do not start with the data model. Usually, when we start designing systems, we have this data model in front of us, and then there's this urge to write service behind every bigger entity we see in this data model. And this is exactly where hell starts. Because then for every user interaction, we have to reach out to this and this and this and this and this and this service. We don't want that. I mean, if we don't have that, we have the data replication reconciliation price to pay. But hey, here's David, hire him. So, yeah, I mean, there are many ways to solve that problem. Reactive is one way. It's a good way. There are also other ways to solve that. Depends on your situation, but it's a solvable problem. It's not a trivial problem, but it's a solvable problem. And the point is, do you want to have a system which is available in production, but not so easy on the replication layer, or do you want to have easy data storage, but your customers hate you? I mean, so what's your business? So, and what's the reason for you being in business? Satisfying your customers or having a perfect data store? It's quite straightforward. Okay, idea number 2 is short activation paths. These long call chains, internal call chains, screw up your availability and increase likelihood of failure, so try to keep them short. And now you get an interesting counterforce. I mean, that's what I like about architectural work, is you always have opposing forces and you have to balance them. So there's not the right solution. Everything costs something. And here you try to minimize the number of remote calls. At the same time, you try to split things apart, so to create isolation between system parts. And hey, where's the sweet spot? Or do I find a very different kind of design technique which allows me to optimize both of them in some way, to a certain extent? Again, there will never be a perfect solution, but here's a way to think of. So if you know that you need any number more higher than 3 remote calls internally to satisfy an external call, you're on a bad road. So these two ideas, for good service design, look at the behavior first, not the data. I've got a whole talk of mine linked in here, which you also can download on Speaker Deck for more details about this idea. And I'm also frank enough to also talk about the trade-offs that you get from this approach. So the data reconciliation trade-off that you have. And the last thing, already mentioned it, be wary of reusability. Reusability is the tightest form of coupling imaginable, because functionality that a service needs to do its work, it's outsourced to a different place. Inside a process boundary, that's a good idea, because if the thing that you're calling dies, you're already dead too. So you don't care anymore. That's okay. It makes reasoning about the behavior of the system a lot easier. But right here, you have the situation that if that one over there dies or has some other kind of problems, you're still alive and you expect an answer. So reusability is, and reusability already or immediately, because it's part of your inherent logic that you need to execute to answer external requests, it brings you back to synchronous communication. You can't go for reusability on an asynchronous way, because here is my core logic, oh, here's part of that, it's out there, and so I send over a request, and I don't care for the next 10 minutes, but my caller expects the answer in 500 milliseconds. It doesn't work. So even if you use an event bus in here, so you expect the response must be back here in 100 milliseconds, hopefully, because otherwise I'm too late over there. So, bad idea. And leads to very bad slicing of functionality, which will immediately drag you into distributed hell. So it rarely pays, because all these business cases will say, yeah, we need reusability because it will pay for itself, because we have all these reusable services then, and so we can reuse, become faster, more flexible. On that level, where you're creating these services, reusability is usually not happening so much. Usually don't reuse these things very often, or you slice them like shit. These are the two options. So reusability is a great thing inside process boundaries. So libraries and so on. So I don't want to recreate some string classes like I had to write for every new project in C++ in the early 90s. I also don't want to rewrite my own collection classes like I had to do back then. I also don't want to write a HTTP server, even if it's fun and to some degree. I mean, it's great. I just take that framework or library and 2 lines of code and it's running. That's cool, but all these reusable things that we need are usually there. They're in our ecosystems available. Look there. And the other things are usually not worth being made reusable. So it doesn't pay so well, and it leads you the wrong way. So go for reusability, compromises your availability and response time by design, and value of reusability in fast process boundary. I also linked a slide deck over here where I went through the whole reusability thing a lot. Hey, I'm quite good in time, so we even have time for the extending the options part. Didn't expect to be that fast. Cool. Really, I'm a lot slower. Yeah. And extending the options is, think a bit about the communication paradigm you're using. In terms of, we have different communication paradigms we can use: request, response, messaging, events, and so on. And they influence a lot which resilience patterns we use. Timeout management or timeout control in the event-driven system is a lot different than timeout control in a synchronous request response and so on. So it's quite different. And maybe we won't look for timeout in an event-driven system so much, but more about eventual completion of the flow or something like that, and blah, blah, all these things. But they also influence the functional failure unit design. What functionality do you put in where? And this is very often underestimated, how much it influences you. Just to give you an idea, let's just take synchronous request response, so REST calls, HTTP, and events on the other hand, messages somewhere in between. So request response gives you more like an horizontal slicing. So you have this functionality where you call in and then you say, well, yeah, let's decompose that a little bit into smaller parts, which we call, let's decompose that. So call stack thinking, basically, how we design our systems internally. Call something, wait for the response, call next thing, wait for the response, and go down and up and compose, so composing things. On the other hand, on the other side, if you design your system with events, there's a different force in slicing your system. And more likely, so there's no guarantee for that, but more likely you end up with something like that. There's an event, you create some piece of functionality which processes some stuff, and then says, okay, I did my stuff, and I emit another event. And then some other pieces pick that up, and some other pieces pick that up. And then eventually maybe there's something at the end which emits the final result. So it's more like a go with the flow slicing, the vertical slicing, so that you can put vertical bars between those things. And it's so, and the functionality which is in that services and which is in that service is quite likely different. And by the way, usually we're better off over there in distributed contexts. So, and it has also some more properties. So we had here this decomposition. Coordination is usually with the request responses more built-in logic and orchestration, which we use, so external orchestrators. The other thing is more likely leads to event change and choreography. On the transaction level, so logical transaction is that you have to build that in, so coordinate all these things that everything works. And event-driven, you more likely go with external supervision. Error handling is then more with an escalation strategy on the one side and built-in error handling on the other side. And separation of concerns is also different. Encapsulation is different. And still, from the complexity side, neither is better or worse. You get different, very different properties, and it gives you different options. It depends a lot on your use case, which one you want to have. Again, in distributed systems, the event-driven and also the message-driven usually gives you a little head start. But the key message here is the communication paradigm influences your functional service design, the options you have to slice your functionality a lot, and the resilience patterns. And I see way too many projects which say, yeah, whatever. In the past, always, well, yeah, we use REST. Why do you use REST? Yeah, because that's how the internet works. So you write an application for hypermedia, documents, and so on. No, we write an e-commerce. I don't get it. Or we use, these days, Kafka. I mean, Kafka is a cool technology, but it's also a hype. So, and a lot of people don't distinguish that. So there are people who really know, here is the place where Kafka is great. And then you should use it. But you shouldn't use it because somebody was there and telling you just, oh, that's a cool thing. And by the way, I'm a developer advocate from Confluent. And yeah, they're doing a great job. They're cool people. But distinguish the hype and your problem. So also true for all other things and technologies and choices. So there's nothing wrong with these things and nothing right with these things. It depends on your context. But be aware of that and don't limit your options up front. So don't say, we are going with this communication technology just because that's the way it's been done or something like that. What's your problem is the question. And then think about the technology, and because it gives you different options. So, I mean, sometimes there's a context given which says, okay, everything in here is written like that, and therefore we should rather go with that. But that's a different situation. Okay. Hey, we're already at the end. Cool thing. Wrapping up. one of the messages I tried to give you in this talk. Message was, QA systems are distributed, failures will happen, they're neither avoidable nor predictable, and so you better embrace your failures and go for resilient software design, trying to identify them and try to fix them or mitigate them. And be aware that the functional design, which parts of the functionality you put in which parts of your system, is crucial for the robustness of the resulting application of the system that you create. It's not only the technical measures you put in. This is where the story starts. And if you get this one wrong, all the other technical stuff will not save you. So you have to get this one right. But the point is, it's poorly understood, it's massively overrated, and it's very different from what we learn. So be aware, there will be dragons on the way. And communication paradigms extend your options, basically, how you can slice your functionality. So, sorry about that, but still, we must relearn functional design for distributed systems. And that was what I had for you as a message. Thanks a lot.